Good morning, everyone. Today we have a very informative session, or I guess the speaker for today is Parsa Bagherzadeh. Parsa obtained his PhD in computer science from Concordia University under the supervision of Professor Sabine Bergler, and he was a member of the computational linguistic at Concordia. In his PhD, Parsa focused on the integration of external knowledge sources for language processing, specifically biomedical text processing. Parsa has a master in AI from Ferdowsi University of Mashhad in Iran and a bachelor in computer engineering from the University of Birjand, Iran. Currently, he is a postdoctoral fellow at McGill University, where he focuses on natural language processing techniques to leverage clinical text report for cancer treatment outcome prediction. I'd like to invite Parsa to start the talk. The stage is yours.
Thank you, Dr. Malki, for the introduction. Hello, everyone. It's good to be here. First, I want to thank Dr. Malki for inviting me to be a speaker at the workshop. So I guess this slide has no use since Dr. Malki already introduced me. Yes, here at McGill, I'm focusing on medical informatics and natural language processing applied to medical texts. So let's talk briefly about history of artificial neural networks. So it all started in the 40s. And so ANNs, or artificial neural networks, are basically inspired by biological neural networks and the neurons that we have in our body and in our brain. So the first attempt was by McClock and Pitts, that they created and proposed a mathematical model of how a neuron might work in our brain. So that was a very simple mathematical model of a neuron. Later in 58, Rosenblunt proposed the perceptron algorithm, which was basically one of the best models that was available at that time. In the 80s, until the 80s, the training was limited to single layer neural nets, but at the 80s, because of the backpropagation algorithm and the introduction of backpropagation, the community could train and learn multiple layer neural nets. But unfortunately, in the 90s, what we call the AI winter, ANNs fell out of the favor because that the community were having a difficult time to train deeper neural networks. But in mid-2000s, a renewed interest was found for deep models. And then 10 years later, models such as generative adversarial networks, autoencoders, and transformers, they revolutionized the ANN's community. And now we are seeing their products such as ChatGPT that is everybody's basically using these days. So, but first talk about a single layer feed-forward net. So let's go back to the history. So what is a single layer feed-forward net? So a single layer feed-forward net is basically a simple projection, a matrix W. So it's a matrix W, which has a size of D of N, D of in times D of out. It projects an input vector, which we here show with X, to an output Y. So the size of this vector, this input vector X, has D of n dimensions, and it's being projected by W to a Y output. So mathematically, the notation is like this: Y is a function of X times W. And note that all of these notations, Y, X, and W, they are vectors or matrices. So Here we see that X is multiplied by a matrix W, and we have an output Y. So for now, let's assume that this function F here that we have, it's an identity function. So what an identity function means, it means that it performs no transformation and no alteration on this product. So XW is basically preserved. The same result is preserved and is considered as Y. So for now, let's assume this. So one quick question that anybody might have is why these are called neural networks if we have a bunch of matrix multiplications. So if you see when you are multiplying the input here X by this matrix W, we are actually multiplying this row by this column, right? So the dot product of this row by this column. It means that this the first dimension is multiplied by this dimension, the second by this one, and so on and so forth. And the result is summed to make up this dimension. So you see, you have a net-like connections here, like you have a net-like connections here. So which we further abstract to something like this. The input is projected to a by a weight matrix to an output. But what is the output and why we have two outputs or one output, or we might have more? It's I will talk about it later. So for now, let's go to TensorFlow Playground. So let me share my whole screen, because if I want to switch between different things, that would be much easier. I'm having a hard time here to stop my sharing.
Feel free to stop the sharing. It's okay.
Okay. So let's go and go to the TensorFlow Playground. So just let's take a break here. Can you see my browser here? Everyone? Yeah. Okay. So TensorFlow Playground is a visual tool that it allows to look at different neural networks and feed-forward neural networks and how the training and how basically it is done. So here in the TensorFlow Playground, it is provided by Google. In TensorFlow Playground, we can construct a simple neural network and see what is actually going on. So the purpose of a neural network or any kind of a classifier is basically find a discriminator line or a separator line or a hyperplane or a surface between two or more classes. So here we have two classes. There are two samples denoted by different colors, orange and blue. And the purpose is here to find a discriminator or a separator that separates the two classes. Here you can see that it can easily find a separator between the two classes such that all of the samples from one class are on one side of this separator, and all of the samples from the other class are on the other side. But this is a very simple case that the samples are linearly separable. How about a case like this? The samples are not linearly separable. It means that the samples cannot be separated by a line or a hyperplane. If I start the process of training for this neural net, you can see that it's going on and on and on, but nothing is happening. It cannot find any separator for the two classes. So now let's go back to our slides. So this motivates to have multiple layers and multi-layer feed-forward networks. So in multi-layer feed-forward networks, we have consecutive projections. So rather than just having one layer that projects the input to the output, we have multiple layers. And so here we have made our network deeper. If we increase the number of layers, we are making the network deeper, and that's where comes the deep learning term from. So here, the first layer, using a matrix W1, it projects the input to H1. Again, I'm mentioning all of these notations are in vector spaces, so H1 is a vector. Then H1, here we have the hidden H1. Here it is projected by W2 to H2. Here we have another projection to H2. And finally, H2 is projected by W3 to Y. So instead of having one or a single projection, we have multiple projections. Here we have increased the number of parameters in this network. So each of these projections, we are considering these W1, W2, and W3 as the number of as the parameters for this network. So and these parameters are trained during the training process. They're learned during the training process. And by making this network deeper, we are hoping that we are giving the network more discriminative power, such that it can basically discriminate more sophisticated distribution. So if I go back to, again, my TensorFlow playground, here I can add more projections or more hidden layers to this network. I can add more we call it neurons here. So I have made my network more complex and deeper. And we are hoping that we can now discriminate the two classes. So let's try to see whether we can discriminate the two classes. It seems that that didn't help. So, and even though we have deepened the network, nothing is happening. The two classes are not getting separated. So the question here is, did we actually increase the learning capacity when we deepened the network? So the Y that we have here, the Y that we had in this slide, this can be rewritten as this. Remember that Y was the product of H2 times W3, and H2 itself was the product of H1 W2, and H1 was the product of X W1. So we can rewrite it like this. And we can actually substitute W1, W2, W3, W1, W2, W3 that we have here with a W tiled. And we can rewrite the whole projections, the whole set of projections to Y equals to XW tiled. So what does it mean? So this was the form of a single layer network. We actually, the multi-layer network was reduced to a single layer network. And we just, on the TensorFlow playground, we just saw that deepening of a network does not necessarily lead to more learning capacity. It doesn't necessarily mean that we have more discriminative power. So at the beginning, we had an assumption. If you remember, here we assume that this function here is an identity function. And actually, this equation is a linear equation. So now let's change that function to activation functions. So what are the use for the activation functions? Activation functions, they can add nonlinearity to a network. What do we mean by nonlinearity? It means that now it can approximate nonlinear functions. So here I'm providing and I'm showing you three very well-known activation functions. Hyperbolic tangent. Hyperbolic tangent squashes or maps its input to the to 1 and -1, so -1 and 1 interval. So any number that you give to tangent, a hyperbolic tangent, it squashes that number between -1 and 1. And we have sigmoid. This is perhaps the most well-known activation function that people have used for many years in deep learning. It squashes, or it maps the values between 0 and 1. And you can see it has a turning point at 0.5. And finally, we have the ReLU activation, rectified linear unit activation function. Overall, this is a nonlinear function, but piecewise it is linear. So from -infinity to 0, we have 0 for this function, and from 0 to +infinity, we have a linear function. So overall, it is a nonlinear function, but piecewise it's a linear function. So it's piecewise linear. So again, activation functions, when we add activation functions and we don't assume that this f here is no longer an identity function, but rather it's a more sophisticated function like these functions, the network gets the ability to approximate more sophisticated functions. So, and these activations are applied to the output of each layer. So the output of each layer in a neural net, it's basically a vector. And here, if we go back, the output here, the output of the first layer was an H1, it was a vector. The output of the second layer, H2, again, a vector, and so on. So the output, so these activation functions are applied to the output of each layer. So suppose the output of an arbitrary layer is something like this, so -1.0044, and 2 other dimensions. If we apply the sigmoid activation to this, we are applying it element-wise. So it means that we are putting this -1.0044 into this function. We are getting 0.26. We are giving 0.88 to this function, and we're getting 0.7, and so on. So one quick question, what actually defines the output shape? So here, before I mentioned, don't worry about what is the output and how we define the output, because the input that we have, it's coming from the training data that is provided to us. It's not in our hands. So it might be image of a fixed size. It's not really up to us what is the size of the input. And but what is this? What is the output? What is the number of outputs? So the number of outputs, for instance, for a classification problem, the number of classes determines the number of outputs or outputs. So for instance, for a binary classification problem that we have 2 classes, we can consider a single output and use a sigmoid activation at the end. So here the output, whatever it is passed through a sigmoid activation, would give us a number between 0 and 1. If the number is below, if the result is below 0.5, you're assuming that class 0, for instance, was predicted, or class negative was predicted. Or if it is above 0.5, we are assuming that class 1 or class positive was predicted. Or we might have a multi-class classification problem. So if we have a binary classification problem, we can assume a single output with sigmoid activation at the end. But when we have a multi-class classification problem with C classes, for instance, we would have C outputs. For instance, here I have a 3-class classification problem. At the output, I'm applying softmax activation, and softmax activation basically maps these output values to the interval of 0 and 1. such that the summation of these values are equal to 1. So these values are summed up to 1. This reminds us to probabilities, because also probabilities of different events, they are summing up to 1. You never have a probability higher than 1. So here we have a set of numbers, a set of outputs that are summing up to 1, and the highest value would correspond to our class that the model that the class that the model is predicting. And we are corresponding and we are assigning each of these outputs to a given class. For instance, the first output to class 1, second output to class 2, and so on. And how we are taking the softmax? So here we have a vector like this, h1, h2 with d dimensions. We are using this function, this expression for each of these dimensions. So we are taking the exponent of h1. We are also taking the exponent of all of these values, and then we are normalizing this. So this normalizing factor in the denominator allows to have a probability. So now that the network has produced its prediction, we are in the training phase, because at the beginning, all of these parameters, all of these matrices that we have talked about, they are randomly initialized. So what is the actually training process and how the training is done? So once a prediction is made, we need to measure the closeness of the prediction and the targets, because if you remember from the previous sessions that you learned and you heard about classifications and supervised learning, there's always a training label assigned for the training samples. So we use loss functions to measure this closeness of the prediction and the target. So we want to actually see how much good. So a loss function basically reflects the goodness and measures the goodness of the predictions of the model. So we are using this loss function during the training, as I mentioned. So there are a variety of loss functions like mean square error loss function. We have cross entropy loss, we have hinge loss, Hubbard loss, and so on and so forth. So we have a variety of loss functions. And basically the question is, what is the difference between these loss functions? So these loss functions are used for different problems. So depending on what is our problem and what is it is a classification or a regression problem, we are using different loss functions. For instance, MSE loss is often used for regression problems, or cross entropy loss is often used for classification problems, both binary and multi-class classification problems. So in our tutorial today, we are going to use both MSE loss and cross entropy loss, but we first will talk about cross entropy loss. So cross entropy loss is basically used for classification. This is an expression, this is a definition for the cross entropy loss. So the loss is actually measuring the closeness between the target that we have, the actual target that is provided to us, and the training set, and the prediction, the y hat here. I'm denoting it as y hat, the prediction. It measures these two. So the only two arguments that we have for the loss are the targets and the prediction. So it is defined as the sum of multiplication of yc. So here I'm saying, so the summation is from 1 to c. So from class 1 to class c, how many classes we might have? For instance, 4 classes. So first we are going to look at the class 1. So what is the prediction that we got? What is the probability that we got for class 1? So y hat 1. Take the log and multiply it by the actual label that is provided in the training set for us. So, and then we took the sum. Note that since this probability value is below 1, the log value would be a negative value. So we are multiplying the whole terms by negative 1, such that we will have a positive value for loss. Because positive value for loss, it makes more sense. So as an example, suppose that this is the actual, this is the target that we want to have. This is the target that this sample is assigned to. So it means that this sample belongs to class 1. If we had a 0 here and we had 1 here, so this notation is a one-hot vector notation. Only one element in this vector is non-zero. So this one-hot vector notation, if the last element or the fourth element was 1, it means that the target was class 1. And I hope you get the idea. And these are the probabilities that are provided by a given network. So the network is 30% sure that it's class 1. It's 40% sure that it's class 2. 10% sure that it's class 3, and 20% sure that is class 4, and it's the last class. So let's calculate the loss here. So minus 1. So each of these, this number here, this dimension is multiplied by its corresponding number. So basically, we would have some sort of a dot product here. So 1 times the log of 0.3, the log here, the log of y hat, plus 0 times the log of 0.4, plus 0 times the log of 0.1, and 0 times the log of 0.2. So overall, the value of loss is 1.73. So that's the value that this much loss we have for a network. So an interesting fact. Suppose that the network is absolutely sure, and it's 100% sure that of its prediction for a class. So suppose I had a 100% probability or 1 as a probability here, and the rest they had been 0, okay, and the rest are 0. So it means that both y and y hat, they are basically the same and they are equal. So, and when we are calculating the loss, the value for log 0 would be, the value for log 1 would be 0. So, and the whole loss, the value for loss would be 0. It means that when the prediction and the target are the same, we should have the 0 loss. So loss means that if we want to minimize the loss, because I just said at the best case, the network should have a loss of 0. So we should minimize this loss. We should change and adjust the parameters of the network such that we would have the minimum loss possible. And what were the training parameters and the learning parameters of the network? There were these W's that I had here. I had in these projections. So these are the parameters that are randomly initialized in the beginning, and through the learning process and the calculation of the loss, we are updating these parameters such that the value of loss would be minimized. So how to minimize the loss? So note that a loss here, loss is a function of what? Loss is a function of this this prediction. it's also a function of the target. But since the target is a constant value, I'm considering the loss to be a function of w hat, y hat here. And what is y hat? Y hat is a function of the parameters that I had in the network. If we go back, y is a function of all of these parameters that I had in this network. So we can conclude that the loss actually is a function of all of the parameters, all of the learning parameters that I had in the network. And I need to minimize this loss. So going back to Calculus 101, you remember when we wanted to find the minimum of a function, what we did? We actually took the derivative of the function and we set the derivative of the function equal to 0. And then we looked for the solutions and we looked for the places that this function had the derivative of 0. Those that solution was actually demonstrating and showing the minimum for a function. However, this is so good to be, this is too good to be true for neural networks. And this is a very ideal case for a neural network. Why? Because neural networks often describe non-convex function. And actually the loss that we have would be a non-convex function. So what is the difference between a convex and a non-convex function? You see here I have a quadratic function that is also a convex function. So here in the convex function, I have a single minimum, only one minimum this function has. However, in a non-convex function, I have several local minima. Here I have a minimum, here I might have a minimum, here I have a minimum. And so there are multiple local minima. And most of nonlinear functions, not all of them, but most of nonlinear functions, they are non-convex, they have multiple local minima, and they are very, very complex to calculate the derivative like we used to calculate in Calculus 101, and everything was perfect and life was easier. So now it's not the case. So to find these these minimums, because minimum we want to minimize the loss function. We ought to find where the loss function for which training parameters the loss function has its minimum value. We would use an approach that is called gradient descent. So gradient descent, what is gradient descent? Gradient descent is an iterative procedure that iteratively updates the parameters. So based on the current value for the gradient of the loss, so we are showing the gradient like this. This is the notation for the upside down triangle. This is a gradient of the loss. So the gradient of the loss is basically the it is related to the derivative, but the point is derivative is more general, but the gradient is basically it's evaluated at a single point. So the gradient actually shows the decline of a function, the slope of a function, just like the derivative represented. Gradient also represents the slope of a function. So suppose our prediction, suppose the set of parameters are showing an error like this. Here we have a prediction. So we are taking for a current sample, we are taking the derivative, and then using a gradient descent, we are updating the old parameter by this much, by eta, by a coefficient eta times the gradient of the loss. So we are moving to this surface this much and we are descending actually. So we are going down. So it's an iterative operation, and it's an iterative procedure. So by every sample we are going down, and down and down until we are reaching a local minima. So most of these deep learning libraries actually automatically calculate this gradient. So we don't have to worry about calculating the gradient. It's all of these the deep learning libraries, they do it automatically for us. So again, it's an iterative procedure that iteratively goes and updates the parameters. So the new parameter is being updated by a little bit. So it would be changed by a little bit. You're going down and down and down. So note that this gradient descent, it can also be applied to convex functions. So right, if you start from here, we are going down and we stop here. So gradient descent, it has the benefit that it can be applied both to convex and non-convex functions. So, and then we want to actually update. So this update of the parameter that I showed you here, it is traditionally done with the optimizers that again are provided in deep learning libraries to us. So an optimizer is responsible for taking the derivative. So it receives the derivative as its input and uses that gradient as the input, and it updates the parameters for us. So there are various optimizers available, like stochastic gradient descent, SGD, RMS prop, ADAM, ADA delta, so on and so forth. So there are many optimizers available, and each of these optimizers, they have a different scheme for the update. Some of these optimizers are converging faster to a minimum. Some of these optimizers they take longer to converge to a minimum, and some of these optimizers they might get stuck in these flat regions that we usually call plateau, and just don't go and find a better solutions. So that's the reason that we have different optimizers, and these different optimizers, they are using different strategies to escape these plateaus or local minimas to get and to reach a better minimum. So for instance, here you can see compared to SGD that gets stuck in the in a local minimum. Something like ADA delta is converging more faster. It goes toward the local to the minimum much faster. So now let's put things together. Let's actually see how the training of a neural net works. So training samples are provided to the model. They are either provided one by one or in batches. So when we are saying batches, it means that we are giving more than one sample to a network at the same time. But in our tutorial, we would go for one by one training. So the samples are provided to the model, and here for all of the samples we have in the training set, we give the sample to the model, we get a prediction, we calculate the loss and the gradient of the loss, and then we ask the optimizer to update the parameters for us. So using this gradient, this value for the loss, please update the network parameters for us, optimizer. And then this procedure goes for all of the samples in the training set, and usually is repeated several times or for several epochs. So the reason is to let the network see the training samples several times to basically to find a better solution and to further minimize its loss. So This is what usually the training procedure of a network looks like. So now let's implement. So here I've made a notebook. But before going to the implementation, I want to go again to this TensorFlow playground. Here in the TensorFlow playground, here you can see, you can choose the activation. And here, for instance, I'm using ReLU, rectified linear units. And then I try to run it. You can see that now that I have a nonlinear activation function, the two classes are easily separated. Okay. I can also look at other types of distributions. So something like this. Here I can again, these two distributions are not really linear separable, but I'm using a nonlinear activation to basically to separate the two classes, and you can see it can separate the two classes very easily using a nonlinear activation. So the choices here are ReLU, hyperbolic tangent, sigmoid, and the linear, which I called it an identity function. So you can search on Google for TensorFlow Playground, and you can set up your neural network, use different data sets like this. We have the data sets with the different difficulties here. You can try, you can see how increasing the number of hidden layers and number of layers would affect the training process, and what are the other factors involved. You can see it visually here. So now let's go and implement what we have learned today. So for the implementation, so this is a notebook that I have created. I want to share this notebook with you. So let me. I'm copying this link, and I'm putting this link in the chat for you. So you should have access to this notebook that I made in Google Colab. So for the implementation of neural nets here, we would use PyTorch. PyTorch was basically developed by Facebook. It's a very popular deep learning framework and deep learning library that is basically everyone is using it nowadays. It is very good for research purposes. You can implement neural networks very quickly using this library. So we would import. So all of these examples are in Python. We would import PyTorch by this import instruction. So import torch. That would import the whole PyTorch library, and we specifically want to work with the neural layers. And this torch.nn, this sub-library, torch.nn, it provides a series instead of standard neural layers for us, such that we don't have to implement these ourselves. But we can implement these ourselves because PyTorch is a very flexible, is quite flexible, and it provides us with many functionalities. We can implement it ourselves, but so for most of these, we choose to use the standard layers that are provided to us by PyTorch as this NN sub-library. So let's, we want to first implement a single layer with the same steps that I went in the presentation. I want to do the implementations. So here, I prefer to define my network as a class, and each of these classes. They can be, we can have object of these classes, and then we can have different networks trained on different data sets, or different or having different parameters, or so on and so forth. So the first thing, the most important layer that we have in PyTorch is a linear layer. So here I'm making an object of this linear layer in the constructor, or in the initialization of this class, that I'm calling it single layer net. Note that I'm making this single layer net a PyTorch module. We can talk about this later, why we will do this. Overall, it gives us more flexibility, but for now, we will skip it. But I'm making this a PyTorch module. So a single layer net, the class called single layer net is defined here. In the initialization of this class, I am having an object as input layer, and making this object, initializing this object like this, nn.linear. So I'm saying I only want a linear layer. I only want a projection, a simple projection. A simple projection that has 64 inputs. The number of inputs is 64, and the number of outputs are 10. So right now, these are arbitrary numbers, okay? And so what is actually the data type of this this projection? It's basically float, because we are calculating all of our we are doing all of our calculations in float. They are real calculations. They are not integers. They are real calculations. So they are in real numbers. So this is the most simple layer that I can have. Only a single layer. So when we are making the class a PyTorch module, if we define a forward function, this forward function is responsible for actually the forward pass of our network, or that consecutive projections that we saw in our network. So it's just simple as this. It gets the input, it gives the input to the input layer. The input layer provides an output, and we are returning our output. Okay, so this part was the initialization part. So for those of you that have worked with C or C++, or Java, you had something like constructors in Java or C++. This serves like a constructor for this singular layer class. So it randomly initializes this input layer. So here, after I define this class, I'm going to make an object of this single layer. So I'm calling that object model. So I made an object of this single layer. Okay, I called it a model. I'm making a random input of 64, of length 64. So it's a vector. So by this torch.rand n, I made a random vector of 64 length as my input. Why I need to give an input of 64? Because here the input layer takes its input in the shape of 64. Okay, and then I'm giving this input to my model. So when I give this input to my model, if my model is defined as a torch module, here you see it's defined as a torch module, it automatically goes and calls this forward function. Okay, so if you don't have a forward function, so I can't change, for instance, I can't change the name of this. So first let me run this, and then let me show you the output here. So let print output, and let me first import this torch and torch nn, because I've not imported this so far. This needs to be imported because we are using nn here and torch later. So here, this was my simple definition. I gave a random input. I made a random input and gave it to the network. So let's look at these. Look at this. What this input look like. This output looks like. So my output. How many dimensions my output has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The same number of dimensions that I specified here. Okay, so the input in 64 dimensions was mapped and projected to an output of size 10. Okay. Now remember, I mentioned that if you are defining this single layer as a PyTorch module, it would automatically, and you're defining a forward function, it automatically goes to this forward function when you are calling the model like this, when you are giving the input to the model like this. Okay, so let's now change, just for you guys to see, let's change the name of this function. So I changed the name of function to forward underscore. So now it has a different name. So if I try to run the model, you see that it says module single layer net is missing the required forward function. Okay, so you see that here I had a PyTorch module and the forward function here is missing. Okay, so now I'm resolving the error. Now everything is good. So one thing that you can see here is that the output here is not just a simple vector or a simple list. It is actually a tensor. Okay, so we will talk about it. We'll talk about what is tensor later. But note that everything that goes inside a neural network, it doesn't matter what is the type of neural network. Okay, everything that goes inside the neural network or is coming out of neural network has the data structure tensor. So if we want to give something to a neural net that is not a tensor, that would raise an error. So suppose I want to give, for instance, a NumPy array, or so I can talk about it later, but just remember this. So now we have defined a simple single layer feedforward net that projected the 64 inputs to the inputs of size 64 to inputs of size 10. And remember, when we are doing a multi-class classification problem, the output layer is often often corresponds to the number of classes. So, but for now, let's add more layers and make our network more deeper. So before I had only a single layer, only an input layer in my constructor before here. Okay. Now, in the initialization of this class, now I have a multi-layer network. I want to have more layers. Instead of having only one projection, now I have 3 projections. Okay, so one projection here, you can see by the numbers, projects 64 inputs of size 64 to 128. This is totally arbitrary. These numbers are totally arbitrary. And then I have a hidden layer that projects 128 to 32 dimensions. And I have an output layer that projects 32 dimensions to 10 dimensions. Okay, so now these are all of the parameters that I have that I will learn later during the training process. So all of the parameters that are considered in these initializations, not all, most of the parameters that are considered here are trained during the training process. So you can exclude part of these parameters in the training process, but we'll talk about it later. So for now, all of these parameters that I have, this set of parameters, these 3 parameters, they will be trained. Now let's go to the forward function. If you remember, a multi-layer network in the presentation was a set of consecutive, it was a sequence of consecutive projections, right? So here the input, using the input layer that I have defined here, the input is projected to an H1. Now H1 is given to the hidden layer that I have defined here. H1 produces, so the hidden layer when applied to H1 produces H2. And then H2 is provided to the output layer. Output layer produces an output. Then I'm returning an output. But here I also, during this forward pass, I want to show you what is the shape and what is the size of these hidden representations that I have, this hidden vectors here. So let's run this. Okay. Here I have made an object of this multi-layer net. Again, I have a random input. I'm providing this random input to this model. So when I'm giving this random input as an argument, this input as an argument to the model, it automatically, again, because it's a PyTorch module, it's automatically going and calling this forward function. So this input goes through this process. Now here I have two print statements. Two print statements here I have. I want to see the shape of H1 and H2. Here you see this, the size of H1 is 128. The same size that I intended before. Why? Because H1 is the result of applying this input layer to my input. My input was 64 dimensions. It mapped, so this input layer mapped 64 dimensions to 128 dimensions. So that explains why the size of H1 is 128. Okay. And then I gave this H1 as an argument to the hidden layer. This hidden layer projects 128 to 32 dimensions. So that explains the size of H2 here, the size of H2, which is 32. So, but again, although I have increased the number of parameters and I have made my model deeper, again, it is again equivalent to having a single layer. So that's why I would add nonlinearity to this network. So here you can see that I have the same network as before. Here I have the same network, again, an input layer, a hidden layer, and an output layer with the same projections here I have. But when I'm doing the forward function, when I'm using the forward function, before passing H1 to the next layer, I'm applying a nonlinearity here by torch.relu, for instance, here. Torch.relu calls the nonlinearity that is already implemented in PyTorch for us. We don't need to do the nonlinearities ourselves. Most of nonlinearities they are implemented in PyTorch. If you want to define your own nonlinearity, you're free to do so, but you don't have to when all of these are provided. So now H1, before passing H1 to the next layer, we are applying a nonlinearity, torch.relu, okay? And then before passing H2, we are applying another nonlinearity. Here I use hyperbolic tangent, okay? So and then we are passing it to the next layer, and then the output layer produces the output, and then we go on. So let's take a look at this. So again, you can see this has the same size that we have in our previous network, right? The number of output here again is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I have an output of size 10. Okay, but here we have applied nonlinearities to this. I can further apply nonlinearity as well to this output layer before returning the output value. I can say here torch.relu, just as simple as this, and give this give the hidden state. If you remember, the nonlinearity was applied to the output of each layer. Okay, now I have applied this nonlinearity. So look at this, just before running this, I have here negative values, right? If I rerun this, you can see all of the negative values are turned to 0, and I only have positive values. If you remember, if I go back to ReLU nonlinearity, all of the values, all of the negative values are turned into 0, and all of the positive values, they are preserved. Okay, so here you can see, if I change this to hyperbolic tangent, okay, if I run it, you see that again I have what do I have? I have negative values. But for now, I don't need any nonlinearities for this layer, because I already have 2 nonlinearities for the previous layers, and my network is already capturing a fair amount of nonlinear functions. Okay, so this is an ideal network. This is a good network that has a good learning capacity, that is able to capture and to approximate nonlinear functions. Why? Because I have considered nonlinearities here in the forward pass. Now let's go and train an actual network, to train it on an actual data set. So I would use the same multi-layer network, the same object that I made here, this model, for training So for this purpose, I use the image data set that is already available in the scikit-learn package. Okay. So, and you can, let me just take a look at in chats what's happening. Okay. So I would answer the questions later in the Q&A period. I see that you have good. I see that you have good questions. So all of your questions would be answered. So now let's load a training data set. So here I'm using the image data set. So let's take a look at what it actually this data set looks like. It's a set of images, 8 by 8 images. Each image is an 8 by 8 pixel image. Okay, so 8 pixels row and 8 pixels column. So 8 by 8. Overall, here I have 64 pixels. So the 64 here, it seems that it's familiar. Remember, I had a 64 here. So this 64 relates to this 64 that I have here. Sorry. So here I have 2 images, one 0 image and one image that is the digit 5. So here the problem and the task is to learn a classifier that classifies each image to one of 10 classes, 0, 1, 2 to 10. Okay, so if I give this image to the network, it should provide an output corresponding to class 5. If I provide this, it should then provide an output corresponding to class 0. Okay, so here I'm loading this data set. If you remember from the previous sessions where you get familiar with supervised learning and how training usually works, we are splitting our data set to train and test splits. Okay, so and this scikit-learn package already provides us with a function to do it automatically for us. So I'm giving the data and giving the targets to this. So if you look at digits.data, it includes all of the images. It includes all of the images like this, and the targets includes all of the labels associated and assigned to these images. And I'm saying I want 20% of the data as my test set. Okay, so it automatically splits the data for me. So remember, I told you everything that is going inside a network should be tensor. So here, this train data that I have right now, it's a NumPy array. Okay, it's a NumPy array. So I'm converting this NumPy array with this torch.tensor to a tensor. So I'm making a type conversion here, just like we used to do float to integer or integer to float or so on. Here I'm converting a NumPy array to a tensor. Okay. So I'm doing this for the train data and test data and only train labels. Why? Because I don't need test labels for the training purpose. The test labels, they should not be disclosed until the end of training process. They should not participate in the training process. Okay. So first I loaded the training data. I loaded my training data. And then remember, I should have a loss function that basically measures the closeness of my predictions and the labels. And also I should have an optimizer. Here I'm choosing Adam optimizer, which is one of the very popular optimizers that is out there. You can look at other optimizers that you have in PyTorch in this sub library, optim, torch.optim. It includes many other optimizers like SGD, RMS prop, and so on and so forth. So to this optimize, so I'm making an object of the Adam optimizer, and I'm giving the parameters of this model. I'm giving the parameters of this model to this Adam optimizer. So again, let's go back to our model here. Again, since I have defined this multi-layer network as a module, as a PyTorch module, all of these, these parameters that I have listed here in the initialization or in the constructor of this class, they are automatically considered as the learning parameters of my model or as the parameters of my model. So when I'm here saying a model.parameters, it would return all of those parameters that that should be learned during the training process to this optimizer. It gives those parameters to the optimizer, and then the optimizer is responsible for updating those parameters with the learning rates. So I will talk. I didn't talk about learning rate in detail, but I will talk about the learning rate more in detail. What is this learning rate? If you remember here, when I was talking about the loss function and the gradient descent, I said by step size. So you are moving on this surface. You are changing the direction on this surface. You are moving your position on this surface by a step size. How much to jump at each iteration? Okay. So that's where the learning rate matters. So let's actually look over the training data, because our what is the training procedure for a model? So looping over the training data. So here I'm looping over the training data. I'm saying loop over the whole training set 5 times. Okay. And in this, so I have an outer loop that is responsible for number of epochs, how many times go over the training data set. And I have an inner loop that goes over the training samples one by one. Okay. So for now, so here I have a model.zeroGrad function. For now, let's forget about this. I will talk about this at the end, why we need this to put this model.zeroGrad here. But so for I in the range of the training data that I have, so whatever I have. So the first training set, the first sample would be the training data of I, training data 0. I'm giving that sample to my model. The model makes a prediction. Okay. The prediction, then I have this prediction. I have already defined a loss function, cross entropy loss here. So the loss function, as I mentioned, it measures the closeness of prediction and the actual training label that I had. Okay, so this was the training data. This is the training data. This is the training label. You can see the training data here. You can assume it as X, and the training label as Y. That basically needs to be predicted. So this loss function, it would have a value. Then using this backward function, I'm calculating the gradient for the loss. So there is so much going on in the background in PyTorch. How this backward function works, it's not the topic of today's discussion. But so it basically, if I wanted to put it simple, it basically calculates the gradients with respect to this the gradients of this loss with respect to the prediction and that we had. And note that the prediction was a function of all of the learning parameters. Then optimizer.step. Then we would say, now optimizer, you are responsible to update the parameters of the network. Here at the end, I'm accumulating all of the loss values over all of the loss values that I have observed for all of the training samples. And at the end of each epoch, I'm averaging all of the losses, and I'm reporting all of the average loss to the user for them to see whether the loss is going down or not. And we'll talk about what does it mean when the loss goes down, or it goes, sometimes it goes up, or sometimes it doesn't move, or it doesn't change. What does it mean? So now let's loop over the training sample. So here I promise you to talk about this model.zero grad. When I'm having this backward function, there are a set of gradients corresponding to this sample, for this sample inside the model. The gradients are saved inside the model. Before going to the next sample, I'm just resetting this model's gradient, and I'm setting all of the model gradients to 0 basically, because I don't want to accumulate the gradient of previous samples for the current sample. Okay. So that was the duty and the purpose of this model.zero grad. Okay, now let's loop over. So here I have, let's go for 10 epochs. I'm looping over the training samples for 10 epochs. Let's see. Yes, I didn't execute this block, this cell. Now I executed this cell. Let's loop over the training samples. You see, I'm looping over the training samples. Here you see that the value, the average value for the loss is decreasing: 1.5, 0.7, 0.47, 0.31, 22, 16, 12, 0.9, 0.7, and 0.5. So you see, the loss is going down. What does it mean? It means that you're able to train this network, and the network is trying to learn this problem. Okay, so and see, we had 1,437 samples. So but one before continuing, just one thing here. I had, how did I give this image to this network? Because I always I always mention that X, the input, is a vector. How did I give this matrix to the network? And I mentioned that the input size for the network is 64. Here I have a 8x8 matrix. So traditionally for feed, when we use feed-forward networks, they operate on vectors as inputs. So if we want to give an image or a matrix as the input to this network, we need to reshape this matrix. reshape it and convert it into a vector. So we are putting all of these rows. We are concatenating all of these rows in a single row of 64 dimensions, right? So from 0 to 7, and then this row 1 would come here. It would constitute 8 to 15, and then from 15 and so on. So we would have 64 dimensions. So this concatenation and this basically vectorizing is already done by scikit-learn for us. But if you yourself want to provide images to a feed-forward network, you need to vectorize it itself. And if you are familiar with NumPy library, you can easily do it with the NumPy library. So the procedure is the same. So I just wanted to mention that that's why I had the size of 64 as the input to my network, and I had 10 classes. I had 10 classes here, which was the size of output. I mentioned that for multi-class classification problem, you should have the same number of output as the classes. Okay. So now that we have trained our samples, now let's make the predictions on the test set. Okay, because right now, yes, our loss has gone down, but sometimes that does not mean that we did a good job. Okay, there are many issues like overfitting in neural networks, and also in any machine learning predictive model. Okay, but so we need to evaluate our model on a holdout test set. Okay, so the same way that I looped over the training samples, I will loop over the test sample. Okay. Here I'm using torch.nograd. It means that just so we are declaring here that we are not interested in saving any gradients because we are not in the test phase. Okay. So this is just a declaration. This has more memory benefits, and not necessarily technical or deep learning or predictive reasons. It has only memory reasons that we are putting this, because if the model is still in the training phase, it would allocate a space to save the gradients that we have. But here, because we are at the test phase, we have no gradients. Okay, so I'm looping over the test data. I'm giving the test data one by one to my model. I'm getting a prediction. Then I'm getting the prediction, and I'm using the argmax on that prediction. Okay, so what is the argmax? Remember, I mentioned that how we are getting the predictions out of this out of a network, because I had 10 outputs. These 10 outputs, each of them, they had a probability, right? So the output with the largest probability was that corresponded to a given class. That was basically meant that the model is predicting the corresponding class. Okay, so here we are determining the output, the index of the output with the largest value. Okay, so and we would have a prediction. The prediction either would be 0, 1, 2, 3, 4, or until 9, because we have 10 digits. So 0 until 9, till 9. So then I'm holding all of my predictions in a list. I have all of my targets in the list. Then I'm using a classification report to see how much I have done and what is the performance on each of these samples. Okay, so you can see that it did a pretty good job. So here, these are my different classes: class 0, class 1, until class 9. We have an overall accuracy here. we have an F1 score, which is a harmonic mean of precision and recall. I believe that in the previous sessions, you have been introduced to these metrics, okay? And this support value means that how many of this sample how many of this class we had in the test set. So overall, we had 360 samples in the test set, 38 from class 0, 29 from class 1, and so on, 35 from class, so the 29 class 1, and 39 from class 9. And this network showed a very good performance on this because for zero class, because it's a very easy class. It's very easy for the network and for everyone to distinguish a 0 bit from a 1, okay? Or 6. It's also very easy to distinguish 6. Sometimes it's a little bit hard to for instance distinguish 8 and 9 because sometimes they look alike. It's sometimes very hard to distinguish 7 and 2 because they look alike a little bit. So there are some classes they have more difficulties, that the model has more difficulty for recognizing those classes. For instance, 9. But for the most of classes, we are seeing a very good fun score and a very good accuracy. So what does this accuracy mean? It means that out of these 360 samples, 97% of the samples we have assigned a correct label to them. Okay. So my tutorial is almost finished, but I want to briefly talk about 3 other set of neural models, 3 families of neural models that are widely used. For one of these, that is convolutional neural networks, you would have a dedicated session later on. But I would just go. I won't go into details for CNNs. I just want to have a quick introduction. So first, I want to talk about autoencoders. Autoencoders, perhaps it was introduced around 2011, 2012. It was one of the at the time it was one of the breakthroughs, autoencoder. So autoencoder, so far when I trained this model, when we just trained this model, we had labels. Okay. So, but another class of neural nets, they are trained with an unsupervised approach. Okay, so autoencoder, you can see the autoencoder. Here is an autoencoder in this figure. It has autoencoder. It has an encoder part and a decoder part. So the first part until the middle is called encoder, and the rest is called decoder. If you look at this, it's basically another feed-forward network, okay, that you can easily implement this. Okay, so you have how many projections you have to define? 1, 2, 3, 4. 4 set of projections you have to define, and in the forward function you need to pass. You need to call each of these projections and then get the output. But the point is, here we have an unsupervised approach. What is an autoencoder? Is basically we are giving the input here, we are getting an output, and the output is basically a reconstruction of the input. Okay, so at the output we want to reconstruct this input. So one might say, okay, this is a useless thing to do, but it is not useless. So as I will mention, so this model is basically modeled as a regression task. Why? Because for instance, for this input you are providing 2.4. Suppose this input is 2.4, and here the output is 2. Okay, so we want this output to reconstruct 2.4. Okay, so this output is supposed to provide a real number. Okay, so basically it is a regression problem. So for the regression problem, we would use MSE loss is often used. So we would have an input, we would have an output, we would call an MSE loss, and then we would have a loss, and then again backpropagate through the network and reconstruct the input at the output. But what is the benefit of autoencoders? It is often used for dimensionality reduction. So once it is trained, this middle part that people that in the community we usually call it a bottleneck. This middle part is basically it is a set of enriched features, a set of very good features that the network has been able to reconstruct the input from. Okay, so there is a justification here that once the training is finished, these features in the middle, this vector in the middle was so good that we could reconstruct the inputs at the output using this feature. Okay, so and then how we use it for dimensional reduction? When the training is done, we get rid of the decoder part and only provide input to and then we have in a lower dimension we have a representation of the input in a lower dimension. So it is used for dimensional reduction. And I also want to talk very briefly about convolutional neural networks. Convolutional neural networks were originally developed for image data, but since 2014, it's also applied. 2014, 2015 is also applied to textual data, but for now we're assuming image data. So convolutional neural networks, rather than being applied to vectors like we had before here in the input of these feed-forward networks, I had a vector. Remember when I wanted to provide that image to my network, we vectorized the inputs. We vectorized the 8x8 image into a 64 long vector. But here, convolutional neural networks, they can be applied to matrices. You don't need to vectorize. You don't need to vectorize the inputs. So where do we have matrices? When we are working with image data, we usually have matrices, because image data images are basically made up by matrices from matrices. And color images are made up actually by 3 matrices. So how does a neural network works? So remember we had before here, if I go back here I had projections, the projections like W here. This W was a projection, right? In convolutional neural networks, we also have those projections. If you look at this here you have a moving matrix. Okay, this matrix, this 3x3 matrix that you can see, this smaller matrix. Okay, we call this a filter. This filter in convolutional neural network, it slides over the matrix. Okay, and every time we are sliding this over the matrix, we are multiplying the corresponding entries together. So 3x0, 0, 3. I hope you can see this. If you don't, I can zoom in. Yeah, I zoomed in. So here the filter, which was the smaller matrix, it has a set to 9 entries: 0, 1, 2, 2, 2, 0, 0, 1, and 2. So we are multiplying the corresponding entries together. 3x0, which is 0, 3x1, 3, 2x2, 4. So we have how many? 5 here. We have 5 here. So and we are adding these and accumulating these together. So I have 5 here. So it's 0 again. That's 0x2, 0. Another 0 here, 0 here, 0 here. Okay, and 1 I'm adding here, and so on and so forth. Okay, so it slides over my input. The bigger matrix is my input or my image. this filter slides over this input, and it produces another image or another hidden representation. And then again, consecutively, we can apply filters over this smaller image and further get more features and go deeper. And this illustration was taken from Theano documentation. So just for your general knowledge, Theano was one of the first deep learning libraries that was introduced around 2014. Now it's obsolete, but it was one of the best libraries that was available at that time. So this was a very brief introduction to convolutional neural nets. Convolutional neural nets, rather than applying convolution over the input, a vector, we are applying convolution over vectors, or we are applying it over matrices. And finally, we have recurrent neural nets. It's another family of networks. Traditionally, we have only one single input. Remember, we only had one X. But sometimes we might have a sequence of inputs like X1, X2, and we have a different and we have inputs coming in different time steps. Okay, for instance, like text. Text is a sequence of inputs. For instance, can process sequential inputs. This is a text that it can is the input at position 1 or time step 1, processed at time step 2, and so on. So recurrent neural networks, in addition to having an input at each time step, we are having a hidden representation of a previous time step. So the function does not have only one argument. It has two arguments. Remember, when I talked about feed-forward networks here, the function had only one argument. The argument was x here. However, here, my function has two arguments, okay? So you see that at each time step, I'm using h again and again and again. So one can look at it as a network with a loop like this, with a feedback like this. I'm providing x of t, and I'm providing h of t minus 1 at the previous time step, and it's looping over all of these input samples. So we can unfold this recurrent neural net throughout time, so which looks something like this. I'm providing x1 and h0. It produces h1. Then this h1 is given and is provided to the same function. It's not a different function, it's the same function. And x2, it would provide h2, and finally xt, ht minus 1, it would these two would be combined by this function, and it would result in ht. So what is this h? H basically, this h of t basically is a representation of the sequence up to that position. So it provides a representation of the sequence until that position, and it demonstrates a memory-like behavior. This is used for sequence classification, and until maybe 4 years ago, it was the dominant approach for processing sequences and processing language before introduction of attention mechanism. That basically was the building block of BERT. I'm sure that you have seen BERT and other derivatives, and one of the derivatives that came from the attention mechanism was ChatGPT. Okay, so I'm done with my presentation, but I also have a implementation of autoencoders here, but we can discuss this later together. So, and I'm open for your questions, and let's begin the Q&A.
Yeah, thank you so much, Parsa. Can you hear me well?
Yes.
Great. I hope the noise in the background isn't too much. I'm in the cafe right now, but we can start asking questions from the previous. There's a lot of very interesting questions that can allude to future lectures as well. Let's see, where do we start? Okay, I'll start from Anna's question. When you were talking about, when you were introducing the linear layers from the first part of the
Yes.
code, there we had a question. Let's go to the code. Yeah, we had a question on, is the linear layer using some default function to map the 64 dimensions to the 10 dimensions?
So
Yeah, I linked to the documentation of PyTorch so you can see what the function is. But yeah, go ahead, the mapping function.
yes. So as I mentioned, these numbers are arbitrary numbers. And when I talked about the number of inputs and outputs, I mentioned that my number of inputs. So Eugene, can you mute yourself?
Yes.
Yeah. So when I talked about the number of inputs that I had, remember my input, the data set that I was working on had 64 dimensions, right? I vectorize, I use vectorized version of this image. This image is 8 by 8. So, and I vectorize that 8. So I have overall 64 entries here in this matrix. It would be a 64 vector. So that would explain the input for this linear layer. How many classes I had? I had 10 classes because I had 10 digits, 0 to 9. And if you remember, I mentioned that the output layer, when we are doing a multi-class classification problem, it corresponds to the number of outputs corresponds to the number of classes. So it is not a default. It is not default. And as Eugene suggested, you can always look at this, the documentation that is provided by you in PyTorch. So I search PyTorch and then .linear. Here you can see that it gives you the more detailed information about this layer. Okay, for instance, how many, so size of each input sample, size of each output sample, you can see that it is provided here to you. And here it's the same. For instance, here in the documentation of PyTorch, it says 20 dimensions as the input and 30 dimensions as the output. Okay. So, but it's always a good idea to take a look at PyTorch documentation if you feel something is not really familiar to you. So, I hope that I could have answered your question.
Great, thank you so much. We also have a couple of questions regarding how you choose the number of neurons and how you choose the number of layers and so on and so forth.
Yes.
In particularly, one question regarding why are we mapping 64 dimensions to 128? Why are we increasing the number of dimensions in the hidden layer and so on and so forth? Yeah, go ahead.
Yes. Okay. So the short answer to your question is that this has to do with how much experience you have with working with neural nets. But overall, so I will talk about this. So these numbers that you can see, so apart from the 64 that I had, because it was defined by the input that I had, right? I had the input of size 64. That was not up to me to choose. And I had 10 classes. So again, the input size and the output size, they are not up to me. But it is up to me to what to choose as these intermediate layers and how many neurons or how many what is the size of what are the hidden sizes. Okay, so usually it really depends on the problem that we have, on the difficulty of the problem that we have. So usually we'll start from few layers. Okay, so let's not talk about the number of neurons at each layer for now. So right now I want to talk about how many layers I have here. Okay, for instance, this TensorFlow playground. Okay, so I have one layer. Okay, here I have one layer and the activation function for this layer is ReLU. So here I know that my network is having nonlinearity. Okay, so if I try to start my training, okay, you see that it starts to learn something, but you see the training loss is barely going down. Okay, I can zoom in here. You see the training loss here. This is the same loss that we had before, right? Remember that we tracked the loss for each epoch. The training loss is hardly moving. Okay, this is because the network that I have defined right now, it doesn't have good learning capacity. It doesn't have a high learning capacity. Why? Because this distribution is a very difficult distribution to learn. Okay, the two classes are very difficult to learn. So here I would increase the number of hidden layers and actually increase the number of the learning capacity. When I'm increasing the number of hidden layers, okay, I have increased the learning capacity. So if I start, you see that now the training loss is going down, right? The training loss is going down. And you see it starts, so it doesn't do a good job right now, okay? But at least it's learning to discriminate the two sets, okay, and the two classes. So getting back to your question, how can we know that how many layers should we have? We should always start from the simplest model. Having one hidden layer, that would be a simplest model. Trying to track the training loss to see whether the training loss is going down or not. If the training loss is not going down, it means that our network doesn't have a good learning capacity. We need to increase the learning capacity of the network. So we need to add more projections to the network to add more learning capacity. So, and also in each layer, if we also increase the number of neurons, okay, we are increasing again the learning capacity. Why? Because each of these neurons, they correspond, because they are connected to the previous layer with a weight. As many as neurons that we have more weights, okay, and that's again the number of parameters, the number of training parameters, and the learning capacity. So, but overall, if I change, for instance, if I change this 128, if I change this to 50, okay, so here you see that. So let me change it to the next one. So here I want this 128, I'm changing it to 50, okay? And then this 50, I'm changing it here because it should be compatible. 64 to 50, 50 to 32, 32 to 10, okay? Let's recompile this. Let's do the training again, okay? I just want to show you that sometimes it really doesn't matter how many neurons we have considered there, okay? Here you see that it's again, the loss is going down, right? The loss is going down, but it's not going down with the same pace, because before we had more learning capacity, because I decreased the number of neurons. We had more learning capacity. The network could have learned more faster, but I have decreased the learning capacity. The network, it takes more epoch for the network to learn. But if I make this prediction, you can see that still I'm getting a decent results. Okay, so that's why I said these numbers more are when I was introducing, these numbers were arbitrary. But overall, these numbers are related to the learning capacity. These numbers are related to the loss. If you want to increase the learning capacity, if you are seeing that your loss is not going down, you need to add more layers, you need to add more neurons, and these are basically are called hyperparameters of your problem. And these hyperparameters, these numbers should be fine. You should find these should be found. We should find these parameters. Okay. So by trial and error, and there are also other other approaches and other tools that help you to find these hyperparameters, but for now, you're assuming that we have to find these parameters by trial and error. So these are hyperparameters, the number of layers and number of neurons that we have in each layer. These are called hyperparameters that we need to define it ourselves. It usually doesn't have a instruction. There is no pre-instruction available for this. So I hope I could have answered your question.
Absolutely. Thank you so much. I really liked your answer. And I think Farhad has also provided some of his comments in the chat as well. And then I see that Amna has a follow-up question that is also very relevant, is that how do we know this network is at a good learning capacity? Is there a metric or use for this? And I think when we look at the TensorFlow playground, people would always do these, monitor these train and validation loss curves as you train it. But yeah, please elaborate further, Parsa, if you'd like to.
So the most important thing during the training, the most important thing during the training that we have and the tool that we have that you are doing good or not is this average loss value. This is the most important thing before any other measures. There are a variety of measures that we can use, okay? But if we want to first set up our network, we need to look at the average loss, because apart from what our performance would be on the test set, because I measure the performance on the test set later, okay? What is the performance on the test set? Our network should be able to learn the training data. And an indicator of learning the training data is having a lower loss, because our objective is to minimize the loss and to have the least loss as possible. Okay, so if we are not achieving our objective, that the main objective in a neural net is to minimize the loss. Okay, we should not care about with the rest. And when the loss is not going down, okay, it means that we don't have learning capacity. So increase the learning capacity. So have an initial configuration, and usually this initial configuration, it really has to do with how much experience you have. Okay, so for instance, somebody that has done deep learning for 6 months or a year, they know. They have a rule of thumb for these things that start from what initial configuration. But nevertheless, deep learning is for everybody. And first have an arbitrary initial configuration, then try to train your model, look at the loss value, see whether the loss value is going down across different epochs. Okay, if it is not moving, or the movements are slow, there are two factors involved here. Either your learning rate is not good, your learning is you have considered a very small learning rate, okay? And the movement in your parameter space, if I go back to the optimizer slide that I had, the movement in your parameter space is very small. You see it's very, very slow. It's very slow, okay? And either your learning rate is not good, so you can change your learning rate to speed up the training process. Sometimes you are changing and you are using many different learning rates, but again, the loss does not go down, or even sometimes it goes up. I will tell you why the loss might go up. But so you need to increase the learning capacity. Okay, so the most important tool that you have to start training, okay, and to improve your training is the learning capacity. So always look at the loss, and then you can also have a third set. So here I only had 2 sets, one training set and one test set. You can have 3 sets: one training set, one validation set, and one test set. In the so you are using the training set for actual training, At the end of each epoch, you are evaluating your model on your validation samples, just like I did on the test sample, the same way. You are evaluating it on the validation sample. And you can also, in addition to the loss, the training loss, you can record, for instance, the accuracy on validation set or F1 score on validation set, okay? And that would give you more statistics and more information on how your model is doing, okay? But the most important tool and weapon that you have for your training, for monitoring your training, is the average loss. And you can see that here in TensorFlow Playground, it also records the training loss, okay, as the most important thing here. You see the training loss is going down when the training loss, and if you plot it, you have something like this. The training loss is going down. You might need to increase your learning capacity if you feel that after a point the training loss is not going down. But overall, this poor network is learning to distinguish between the two classes. And how do I know it? I know it because the training loss is going down. And one important thing here, you see that sometimes the loss is going up, okay? After a certain point, the training loss having some sort of isolation. So what is the reason? Sometimes if you choose an improper learning rate, you might go up to this curve sometimes, or down, or when you are going down, you might go up to a local maxima. So here, for instance, you are going down. If your learning rate is too much, you might jump to this side, okay? So there are many things, many factors involved in the training, but the most important thing is to monitor this average loss. I hope I could have answered your question.
Absolutely. Thank you so much. And I think we have just one last question. If you can provide some resources on understanding attention mechanisms. I personally know that you'll have a lot to talk about for this in particular topic, but if you can send some links, that would be nice. And otherwise, I think we could wrap it up. Otherwise, Farhad, do you have something else to talk about? Or
I know that was a very informative session. These contents and concepts shows up again and again, and a solid understanding of these concepts is very helpful for future sessions. Thank you so much, Parsa, for the great talk.
You're more than welcome. I hope I could have conveyed something. So you can also reach to me if any of you had questions, maybe after the workshop. I can answer. So the whole point of this workshop, as intended by Dr. Maliki, is to have more interactions, in contrast to other workshops that are out there. Here we want to have a more engaged interaction with the students. So you feel free to contact me, and I can share my my email to you. So hold on a second. I'm typing my email here at the chat. You can send me email. So to learn about attention, you can always look at this paper. Attention is all you need. It was introduced in 2017. It revolutionized, without a doubt, it revolutionized the whole field. Let me send it to you. Okay. So I send it. Oh yes, I'm sending it to Eugene. Sorry. Yeah. Yes, Eugene. Thank you so much, Eugene. So this attention mechanism revolutionized the whole industry, the whole community. And if you are using ChatGPT, this is thanks to this paper. So always, so you can take a look at this. It has a fairly simple mathematics. Attention mechanism is beautiful because it has simple mathematics. So yes, and feel free to use this notebook that I've provided. I think let me again Let me again share it with you for you that you don't have it or you joined us later. So I feel free to explore this this notebook. This is a very lightweight implementation for the feed-forward net, and also I provided as a bonus an implementation for autoencoders at the end. Autoencoders, you can see the forward pass has an encode part and a decode part, and here you see that because I use the regression task, I'm using the MSE loss function. So you see that again the loss is it's going down, and the input is trying to be reconstructed at the output. You see that instead of having a cross entropy loss, I'm using an MSE loss because it's I modeled it as a regression problem. So keep your on the website. We might have put materials on the website. So yes, that's it. I'm
Perfect. Thank you
Dr.
so
Malki,
much.
can you force me to stop sharing because for some reason
Sure.